Today, we're diving into something pretty amazing: electrolysis. It's this process where electricity isn't just for powering your lights, it's actually a tool for creating and literally transforming matter. Let's get into it. Yeah, have you ever really thought about it? How you get that perfect shiny chrome on a faucet? Or the pure aluminum for a soda can? It kind of feels like magic, right? The idea that you can just zap something with electricity and pull elements apart and then put them back together in new ways? Well, today, we're going to pull back that curtain and see exactly how it all works. All right, so first up, what is this chemical magic? Because as cool as it sounds, it's not actually magic. It's all about some pretty clear scientific rules. Okay, so here's the core idea. The word electrolysis literally means breaking apart with electricity. That's it. You're basically just running an electric current, a direct current specifically, through something to force a chemical reaction that would never happen on its own. The key thing to remember is that the electricity is the muscle here. It's providing the raw energy to bust those chemical bonds apart. So to make all this happen, you can't just stick some wires in a glass of water. You need a specific setup, and it's called an electrolytic cell. So let's take a look inside and meet the key players in this whole operation. Okay, every single one of these cells has three parts that you absolutely have to have. First, you've got two electrodes. There's the anode, which is hooked up to the positive side of your power source, and the cathode, which is hooked up to the negative side. And then the third piece is the stuff in the middle, the electrolyte. Think of it like a soup that's just full of these free-moving charged particles. The positive ones are called cations, and the negative ones are anions. Now, this next part is a lifesaver if you're ever trying to remember what's happening where. Just remember this little phrase, red cat. It stands for red reduction happens at the cathode. And reduction is just the fancy word for gaining electrons. So red cat, reduction at the cathode. And if you know that, then you know the opposite, oxidation, has to be happening at the other electrode, the anode. Super simple, right? So what does this actually look like? Let's take a simple example, molten lead bromide. You've got positive lead ions and negative bromide ions floating around. Okay, turn on the power. Opposites attract, right? So the positive lead ions get pulled over to the negative cathode. Once they get there, they grab some electrons. Remember, red cat, reduction at the cathode, and poof, they turn into pure liquid lead. At the very same time, the negative bromide ions are zooming over to the positive anode, where they lose electrons and bubble off as bromine gas. And just like that, you've used electricity to split a compound into its basic parts. Now, quick but important distinction here. It's really easy to get this mixed up with an electrochemical cell, which, is just a battery. A battery is the total opposite. It produces electricity from a chemical reaction that just happens on its own. An electrolytic cell consumes electricity to force a reaction. So think of it this way. A battery is like a waterfall generating power, and an electrolytic cell is like a pump using power to push water uphill. It's all about which way the energy is flowing. Okay, so that last example was pretty straightforward, right? You only had two types of ions to worry about. But what happens when we're not dealing with some pure molten stuff? What happens when we dissolve our substance in water? Well, that's when things get a whole lot more competitive. Yeah, this is where it gets really interesting. See, water itself can break apart a tiny bit into positive hydrogen ions and negative hydroxide ions. So now you've got 4 different ions in the mix. The moment you flip that switch, it's a flat-out race. Which of the positive ions is going to make it to the cathode first? And on the other side, which negative ion is going to win the race to the anode? Let's use salt water as our racetrack. So, on your marks, get set, you've got sodium ions from the salt and hydrogen ions from the water, both sprinting for the negative cathode. And at the same time, you've got chloride ions from the salt and hydroxide ions from the water racing towards the positive anode. The big question is, who's going to cross that finish line first? And this race isn't random. There are rules that decide the winner. 3 main factors. First is something called the electrochemical series. You can think of it like a league table that ranks how easily an ion reacts. Second is concentration. This one's huge. If there's way more of one type of ion, it's got a massive head start. And finally, the third factor is the material of the electrode itself. Sometimes the finish line is just stickier for one type of ion than another. And check this out. This is how much concentration can totally change the game. Let's look at the race to the anode. If you have a really dilute watery salt solution, the hydroxide ions from the water actually win, and you get oxygen gas bubbling off. But if you use super concentrated salt water, what we call brine, the sheer number of chloride ions gives them the win. And now you get chlorine gas instead. Think about that. Same basic ingredients, but just by changing the concentration, you get a completely different product. Okay, so this whole ion race thing isn't just some cool chemistry experiment. It's actually the foundation for huge industrial processes that make a ton of the stuff we use every single day. I mean, think about it. The aluminum in your soda can, that's extracted from its ore using electrolysis. Those massive chemical plants that make chlorine and sodium hydroxide, yep, that's electrolysis of brine. That tough, colored finish on your smartphone or laptop, that's a process called anodizing. And of course, electroplating, that's how we get that shiny, protective metal layer on everything from car parts to faucets. So how does something like electroplating actually work? It's surprisingly simple. Let's say you want to coat a plain old key with a layer of copper. Here's what you do. First, you make the key your negative electrode, the cathode. Then you take a piece of pure copper and make it your positive electrode, the anode. You dip both of them into a solution that has copper ions floating around in it. Then you just turn on the power. The copper from the anode starts to dissolve into the solution, and those copper ions get pulled over to the key, where they plate out in a perfect, thin layer. It's pretty neat.
So this ability to just move atoms around and build things with electricity is, well, it's incredible. But, and this is a big but, like a lot of powerful industrial tech, there's a flip side. It comes with some serious consequences, especially for the environment.
Yeah, that same process that gives us that beautiful, shiny finish also leaves behind some pretty nasty stuff. And its environmental footprint, it's a big one. The electroplating industry specifically can create this nasty cocktail of pollutants. The wastewater is often loaded with toxic heavy metal ions, things like copper, nickel, chromium, which are really bad for fish and other aquatic life. Plus, you've got corrosive acids and bases that can wreck drainage systems and ecosystems, and to top it all off, sometimes they use extremely toxic chemicals like cyanides just to get a better-looking finish. And look, this isn't a new problem we just discovered. People have known about this for a long time. Just to give you one example, you can go all the way back to 1993. That's when the Hong Kong government put specific laws in place to get a handle on the chemical waste coming from these factories, forcing them to treat their waste before just dumping it. So here's the thing. Electrolysis is absolutely fundamental to our modern world. It gives us everything from lightweight metals for planes to chemicals we need for, well, everything. So the challenge isn't about getting rid of this amazing tool. The real challenge is about making it better. It's about innovating cleaner, greener ways to do it, so we get all the good stuff without the heavy environmental price tag. So the real question is, what does that future look like?